Another very unique property of the transition elements is the formation of interstitial compounds. So we'll be discussing here the formation of interstitial compounds. See, what happens is very small elements like hydrogen, carbon, nitrogen, boron, etc. when they are mixed in the molten state of these elements, they easily enters into these lattices of these elements and occupies these interstitial voids or spaces. These are interstitial voids or spaces. So what happens is when these smaller elements are mixed with these elements in the molten state and allowed to solidify, these small elements occupies these interstitial spaces and forms non-stoichiometric compounds which are called interstitial compounds. They can be like this: titanium carbide, we can have a manganese nitride, we can have iron hydride, vanadium hydride is 0.56, it can be titanium hydride 1.6. So all these are the examples. Definitely we can't take out oxidation state from these formulas because these are not to indicate this. What we have is these ratios 1.6, 0.36, 3, 4, all these are non-stoichiometric. So because these smaller elements cannot occupy all the voids, but yes, they occupies, and what we find is that they form non-stoichiometric compounds which are called interstitial compounds. Now these compounds are very important and very unique in the sense that they have very different properties. They're additive properties, like they are found to be much more harder, stronger, tough than their normal usual metals because they are less compressible because of these, that the left out spaces also get occupied. Density gets increased. Remember that the malleability, ductility gets decreased, but no change in thermal and electrical conductivity. They remains inert, but they become very hard, strong, very tough. That is what we can find is same thing is an example of a mild steel, hard steel and cast iron. As the percentage of carbon is increased, the hardness of the iron increases. Mild steel is 0.5%, hard steel 1.5%. It can go to up to 3%, becomes cast iron. That's why what we find is the steel is of different types and its hardness increases with the percentage of carbon, because actually with carbon it is forming interstitial compound. The next property of transition element to study is their alloy formation. Yes, they form number of alloys. They can be mixed in any ratios and they form homogeneous solid mass called alloy. The main reason what makes them to form so many alloys is that they have comparable atomic sizes. When their atomic sizes, since they are comparable, when mixed in the molten state, they easily exchanges their lattice positions, and on solidification they forms a homogeneous mass which is called alloy. And that is why we can easily mix copper and zinc in different ratios to form brass, bronze. It can be mixed with other different transition elements to form number of alloys. And let us discuss their oxides and oxyanions. See, transition metals except scandium all exist in MO in the +2 oxidation state and form oxide, and this type of oxide, all of these transition elements are actually ionic in nature, whereas they can go to their highest oxidation state, like we can have vanadium existing VO and it can go up to V2O5. Chromium can form, yes, CrO4 2-, it can form Cr2O7 2-, yes, it can form Cr2O3, CrO3. Similarly, we have manganese which is able to form Mn2O7, MnO2, Mn2O3, yes, and MnO4-, MnO4 2-. So all these are their oxides and oxyanions, and we know the oxides or the oxyanions in which the transition elements are in their highest oxidation states will be what? Will be covalent and will be acidic, and the ones in which they are existing in the lower oxidation state will be ionic and will be basic, because they can be oxidized to their higher oxidation states, and when they are present in the highest oxidation state will always be getting reduced to their lower oxidation states. So these are the usual properties we know about the oxides and the oxyanions.